move on to the next lecture, please. I think the fourth lecture today we have from Professor G.V. Ramana from IIT Delhi. Professor Ramana, you are ready?
Yes, sir. Very good morning.
Morning. I'll just quickly read out a few lines of your CV, though everybody knows you well. Professor Ramana is a professor and head of the Department of Civil Engineering at IIT Delhi. He mainly specializes in geo-environmental engineering, geotechnical earthquake engineering, waste mechanics, and ground improvement. Throughout his career, he has worked as a consultant and expert on various geodisasters, their mitigation and remediation. He holds a PhD from Rensselaer Polytechnic Institute, New York, and I'm happy that he also holds an MTech degree from IIT Madras. Professor Ramana, very nice to have you here on this session, and we look forward to hear your keynote lecture. Professor Ramana, please.
Thank you very much, sir. And in fact, it is almost a pleasure. And all the credit goes to Professor Reddy. And I thank the IGS team for allowing me to give this presentation. And hope everybody is able to see the screen and I'm audible.
Yes.
Yes, great. So, Bagli sir, कितना time है?
It is same 15 minutes, and Professor Dr. Bagli will give you a buzzer after 15 minutes. So you
okay, sir. 20 minutes, so I'll wind it up. So thank you very much, and good morning, everyone, distinguished what you call senior professors and the delegates. Very good morning. This is about a small project I got involved at Polavaram project. This place is close to my native place, and this is one of the large earth dams. What I mean large earth dams, it is not in terms of the height, in terms of the length. This is a quick view of the Google Earth image of the Polavaram Dam project for those of you who can't travel. This is the river Godavari. This is the constructed upstream coffer dam in place as of today, downstream coffer dam, and spillway structures are partially completed. And this is the spill channel in which we are going to have some trouble because of the clay. And this is a small video of the upstream coffer dam that is in place and which survived 2019 floods, for those of you who can't go to the site. And in fact, this is your upstream coffer dam, this is your downstream coffer dam, this is along which the dam is going to be aligned. Between the two hillocks, they give another name. There is a small portion of the dam here, but this gap 2 portion of the dam, which is primarily located in the river portion. It is about 1.75 kilometer long, and the height of the dam is about 45 to 50 meters along that stretch. So, as usual, I got involved here right from the geotechnical investigations. I was lucky enough. DDRP panel, Dam Design Review Panel, and Central Water Commission were kind enough to get me involved. Besides regular borehole drilling and the collection of undisturbed samples and some SPTs. These are very routine tests which we need to have. And beyond that, we did ECPT, electric cone penetration test, and cross-hole shear tests. And the borehole tests were conducted at 3 meter offset, and CPT center 10 meters offset from the cutoff wall constructed by Bauer in place. And we conducted 2 cross-hole shear wave velocity tests. One is 63 meter deep, and the other one is 93 meter deep. So this is the cutoff. The red line there you can see is the cutoff wall axis, and significant number of tests were conducted. And ECPT, This is the diagram I have taken from Paul Main. For some of you, most of the geotechnical engineers are familiar these days. And some of you have not seen the equipment. This was conducted by Keller Company. And it is very routine. I mean, routine test in some geotechnical investigations, including the pore water pressure measurement. And based upon the geotechnical investigations, the main gap 2 dam, a part of that is sitting on sand region, and a part of that is sitting on a clay of high plasticity. I will just show you the profile. This is the Google Earth image, and the dam is going to sit across here. And this is how the data looks like. This is from a bunch of the SPT, ECPT, and tests done by CSMRS and some other companies. The best part it is on the right side, you can see that towards the left bank, it is a clean sand. The percentage of fines are less than 3%. On the left side, we have 3%, it is CH, and the clay is highly plastic. For example, on the clay side, the plasticity index is about 40 to 50, and the liquid limit is as high as 70 to 80 at some locations, and natural moisture content is hovering around the plastic limit. These are the E-log-P consolidation test results conducted by CSMRS through undisturbed soils, which I'm not aware how they got it, but it also shows a high compressibility. And this is the channel, spill channel, which is towards the right bank. I hope you can see a small dump here. This is the overburden mine dump, which these people are dropping there, and it induced a failure all the way down to the river. You can see the cracks here, the pavement broken. Now it is a very close-up shot where you can see it is being clearly seen. And this is a small video of about few seconds only. This has displaced here. This is due to the overloading on the top of CH clay. And ECPT test results, when you get electric cone penetration test results, we have to classify them using soil behavior type, not like a SPT test where we are going to get. So soil behavior type zones are used for interpreting the data and see how well the CPT data is able to capture the behavior. This is a borehole, and this is the soil behavior type from a ECPT test. So this clearly shows that this portion is sand and this portion is clay. So I still can't understand. We still rely upon SPT for our routine investigations. We should move on to CPT. This is another place where, I'm comparing a ECPT test and a borehole close by, and you can see a remarkably nice match. The only problem with CPT is we can't get a test for carrying out some liquid limit or grain size distribution curves. Then another best part is we did 2 crosshole seismic tests by Fugro. One is for 63 meter, the other one is for 93 meter depth. I'm showing the results directly at the 2 chainages. This is at chainage 480, which is 63 meters. The other results are on the lower side, which is at another chainage, but only 70 meters away. But the depth of the borehole there is 93 meters. There is a significant difference between these two. So we need to find why. So what we did is we had extensive set of SPT and we had CPT test data, and we compared the values measured with empirical correlations. You can see here very clearly that at the chainage 480, the measured value and the estimated value are very close to each other. Whereas at Chinese 550, the measured value is significantly lower than the empirically estimated value band. So we decided to disregard the 550 meter depth. They repeated the test, but the values were not coming right. Most likely it is a 93 meter deep wow. So we disregarded data, and this is not considered further in the design. For finding the liquefaction susceptibility assessment, we used the standard procedures available. We followed the NCER guidelines, and the seismic parameters were given by University of Roorkee seismology department. They said consider a magnitude of 0.65 earthquake and 0.18 G. These are the values given by CWC and this one for finding the liquefaction susceptibility at the site. So we try to find the liquefaction susceptibility using, we had 3 sets of data with us. We had SPT, we had cone penetration test, we had cross-hole shear wave velocity. This is a geotechnical engineer's dream. We can compare the values from each other. And another interesting thing is the percentage of fines in the sand are almost nil. It is a very clean sand. The percentage of fines approximately is about 3% in about a stretch of 1 kilometer. And these are the typical N values I found and plotted, but we can see that that's why I don't like N values. Even at 40 meter depth, these are coming very low, which is due to the operator or the way they are doing the test. So SPT, the reliability is slightly on the lower side, and at a 40 meter depth, getting a 20 is very unlikely. So for the liquefaction hazard assessment, average N value is used. We can debate about it, but what we did is we used a factor of safety of 1.5, whether it is going to liquefy or not, using the simplified approach with the developer procedures, all the corrections. So if we use a factor of safety of 1.5, the depth of liquefaction is coming around 16 meters. Is coming around 16 meters. When I went for using CPT, we had 27 number of CPT data, and in fact, we can do a PhD degree here. But what we did is we analyzed each CPT data, and then we averaged the factor of safety. I know this is very crude, but that's how it works in the site. If you start doing risk analysis, and if I start doing probability and everything, engineers won't like it. They would like you to give a solution. So when I looked at it, the depth of liquefaction is coming around 9 meters, considering a factor of safety of 1.5. But with the shear wave velocity, we got into trouble. So at one Chinese, we are getting 24 meters, and the other Chinese, it is coming around 6 meters. So 24 meter depth of liquefaction is due to the error in the measurements. That's what I believe. And we disregarded that value. So we recommended a depth of liquefaction of about 15 meters. But contractually, I think this project has a lot of history, and they said the minimum improvement required is 20 meters. It is required for 20 meters. So how do we improve the subsoil at the sand region? We decided to use vibroflotation technique. And to do this, what we did is, at what spacing should we use? What should be the capacity of the vibrator? And all these trial and errors were conducted. So at one location, we used a spacing of 2 meters center to center. And in another location, we used a 2.5 meter center to spacing. And we carried out pre-ECPT and post-ECPT, before and after. Because when the government wants to pay the contractor, they say, where is the improvement? So these are some of the pre-ECPTs that we used for in situ ground. After vibrocompaction, we carried out 4 post-ECPTs. Now, when you want to use this data, we get into what is the in situ density, unit weight from the CPT. Again, there are a bunch of correlations available in the market, and we used Robertson and Kawal. And this is the unit weight of the ground before treatment. It is about fluctuating between 16 to 18. And here it is 16, and then it is remaining sort of 17 and constant. Then after the post vibrocompaction also we had ECPT data. So we try to look at what is the average profile after. So it is going to be about 18 and 19. But it is very difficult to use these correlations. So this is the pre at 2 locations, and this is the average post at the 2 locations. So there is an increase in density, but it should be converted to relative density. So when we would like to use relative density from the CPT data, there are quite a few correlations available. Kulhave and May in 1990. We used those correlations. So this is the relative density of the in situ. It is about almost 60%. So I don't think there is, the chances of liquefaction would be very low. But again, it is contractual obligation. So vibrocompaction was done, and the post vibrocompaction, the relative density went up to 80 to 90%. Above 80%. So there is an increase in the relative density of the sand post vibrocompaction. This is the relative density before, and this is the relative density post compaction at one of the trial sites. At another trial site, this is the improvement in the relative density. Now, when we told the engineers that you have to follow this procedure, then they wanted, how do I do my construction quality assurance? How do I know that the soil has achieved this kind of relative density? And they told us these relative densities and everything, we are very worried. And what we know is cone penetration test gives me a QC value. So they asked us, give us a target QC so that the ground has a relative density of 80% or more. Then what we did is we went to the literature and looked at different correlations available. Schmettman has given one correlation. Willett and Mitchell has given another correlation. Baldi has given another correlation. So we used all these 4 correlations and tried to tell the engineers what is the target QC which you can check in the field for paying the bill. Primarily, that's what it comes down to between the contractor and the government agency. Now, this is the target QC required to get 80% to 90% relative density using one of these correlations. Using another correlation, Baldi's correlations, for 80% or more, the tip resistance should be more than this. These are all the post. So in these 2 cases, they are completely satisfying. And this is another correlation. And finally, we used Kulhave and Main. So these 4 correlations have different connotations, isn't it? They're not getting the same values, but finally, the engineer said, what should we do? So in the DDRP, they decided that the 4 of them, you should take the average, and the measured QC should be more than this for paying the contractor. And this is the vibrocompaction being carried out by Keller at the site. This is the trial area where we did. And after that, you can see a crystal clear deformation of about 5 to 7%. This is a small video.
I think, Professor Ramana, there is some issue with the playing of the video. Would you like
Really?
to skip it?
Yeah, I will skip it. Yeah. So what we did based upon this is for the vibrocompaction works, I think ECPT is the best method to record continuous monitoring and to verify pre and post engineering behavior of the soil. And at the site where the fines content is less than 5%, I think getting a post relative density of 80% is practically achievable. They did the trials at 2 meters, 2.25 and 2.5 meters, and we decided for a spacing of 2 meters.
So 5 minutes, please. 5 minutes.
Yes, sir. I'm going to wind up in the next few minutes.
Thanks.
So this is the typical ground improvement chart most of us are familiar with. So at Polavaram project, we are sitting on both of them. We are sitting on a CH clay and a poor sand. So it's a geotechnical engineer's paradise, and vibrocompaction has been implemented at the site for liquefaction resistance. And then we are going to do some vibro replacement for the clay settlements to be under control when we make a 45-meter dam. And thank you. And this all work, there are several people, and Professor B. Janakaramaya at IIT Tirupati significantly helped me in some computations. And Mr. Mohammad Rafi, who is associated with the project right from the beginning. Government keeps changing, contractors keep changing, but this gentleman is always with the project, is dedicated to that, from which I'm able to get the data, and Mrs. Keller, who sort of made me available some of the geotechnical investigation data. Thank you, sir.